Every time you tap your phone screen or click a mouse, you're counting on a tiny microchip to perform billions of calculations every single second and to do it perfectly. But have you ever wondered how designers make sure every single one of those signals deep inside that chip gets where it's going at exactly the right time? Well, that's the massive challenge we're going to unpack.
Right. Here's the big question. How in the world do you check millions, literally millions, of different routes a signal can take inside a chip and do it without actually running the chip? I mean, it sounds completely impossible. Trying to test every single possibility one by one, well, that's just not going to fly.
So to really get this, you've got to picture what's happening inside. Think of a modern chip as this giant, sprawling city, and all the signals are like racers in an impossible, high-speed race. They're all sprinting from a starting line to a finish line, and every single one has to get there on time, every time.
And listen, we are not talking about a few dozen racers here. We are talking about millions of these individual timing paths. Every single one has a deadline it has to meet perfectly. Because if even one signal is late, just one, the whole system can come crashing down. The stakes are incredibly high.
So you might be thinking, okay, why not just test them all? Well, the old school way would be to run a simulation. But with millions of paths and an almost infinite number of data inputs, you'd be running that simulation for like an eternity. Seriously, you would never ever finish designing the chip. We need a much, much smarter way to do this.
And that smarter way has a name: static timing analysis, or as everyone in the industry calls it, STA. This is the secret weapon, the elegant and incredibly powerful solution to what seems like an impossible problem. It's a total game changer. So what is it exactly? Well, STA analyzes the circuit statically. What that means is it doesn't need to actually simulate the chip doing its job. Instead, it looks at the blueprint of the chip and just calculates the absolute worst-case, slowest possible delay for every single path. It's a brilliant shortcut to find out if any of them could ever be too slow.
Now, like any brilliant shortcut, there's a trade-off. The huge win for STA is its speed, and the fact that it is exhaustive. It checks every single path, guaranteed, no exceptions. But the catch is that it has its limits. It really only works for what we call synchronous designs, circuits that march to the beat of a single clock. And it's important to remember, it doesn't check if the chip's logic is correct, only if it's fast enough.
And this brings up a really crucial point. You've heard the saying, right? Garbage in, garbage out. Well, that absolutely applies here. The STA tool is only as smart as the information you feed it. Engineers have to give it super accurate rules for the race, what we call timing constraints. If you tell the tool the wrong finish time, you might trick it into thinking a broken path is actually okay.
So, how does STA even begin this whole process? Well, the very first thing it has to do is understand the racetrack. It breaks the entire chip design down and creates this incredibly detailed map of every single possible route a signal can take.
And the basic unit of that map is called a timing path. It's really simple. A path is just any route a signal takes from a specific start point, say a memory element or a chip input, to a specific endpoint, like another memory element or a chip output. It's one leg of the race.
And STA is smart enough to group these into four main types. You've got your internal paths that go from one memory register to another. Then you have paths coming in from the outside world to a register, or going from a register back out to the world. And finally, you've got these simple paths that just go straight through from an input to an output. Every single one gets put on the map and checked.
Okay, so STA has its map with millions of paths. Now comes the analysis part. And amazingly, it all boils down to calculating a single, incredibly important number for each path, a number that tells you everything you need to know, and that number is called slack.
This is probably the best analogy for slack I've ever heard. Just think about a rope. If there's slack in it, you have some wiggle room, right? Some extra length. In timing, if you have slack, you have extra time. But what happens when that rope gets pulled tight? When there's no slack left, it's about to break.
So, to put that in more formal terms, slack is simply the difference between the required arrival time, that's the absolute latest a signal can show up without causing a problem, and the actual arrival time, which is the tool's calculation of the longest it could possibly take for that signal to get there.
And it all comes down to this one simple, beautiful equation. For every single one of those millions of paths, the tool does this calculation. Required arrival time minus actual arrival time equals slack. That one number is the final grade for that path. It's that powerful.
So how does it get those two numbers? It's pretty clever. First,
It calculates the arrival time by moving forward through the circuit from the start, adding up all the little delays along the way. Then, to get the required arrival time, it works backwards from the finish line, figuring out the latest possible departure time from each point in the path.
Okay, so once the tool has those two values for a given path, it can finally deliver its verdict. Is this path fast enough for the chip to work? Is the race a success? The answer is all right there in the sign of the slack.
And it really is this simple. If your slack is a positive number, hey, congratulations! Your signal got there with time to spare. That path passes. But if your slack is a negative number, that means your signal's actual arrival time was later than its required time. The signal was too slow, and that path fails. Period.
This quote really says everything you need to know about how designers feel about this. In the world of chip design, negative slack isn't just a small problem. It's a critical, show-stopping error. It means your design is fundamentally broken, and it will not work at the speed you designed it for. So let's be super clear. Negative slack isn't just a warning, it is a timing violation. It means that data sent out on one tick of the clock won't get to its destination in time to be captured by the next tick of the clock, and that causes chaos, data corruption, system failures, the whole shebang. It absolutely has to be fixed.
So you see, static timing analysis is this brilliant detective. It tells engineers exactly which paths are failing, and even by how much time they're failing. It's an absolutely essential tool. But that brings us to the final, really interesting question. Knowing exactly what's broken is one thing, but how do engineers actually go in there and fix it? Well, that's where the real art of chip design truly begins.